Hi everybody, it's Mr. Gerhardt again, and I'm here to discuss complex numbers with you. We're going to go through a couple different examples and then work a little bit with complex numbers. And it really stems from the fact that we want to be able to solve all equations. And when we have certain equations, we can't solve them because we're trying to square root negative numbers. So mathematicians a long time ago invented complex numbers so that they could solve those. So we're going to go through a couple different problems, a couple examples, and I hope you guys get something out of this and it helps you out. So here we go. The first thing that we're going to do is we're going to try and solve this equation. 2x squared plus 11 equals negative 21. Now, the process that I'm going to use is the square root method because it's the fastest, the easiest, and there's no x term. If there was an x term, I'd try factoring or to use the quadratic formula. We're going to end up using all different types of forms. So this one here, we're going to go ahead and use the square root method, which means I'm going to first get that squared part by itself. First, by subtracting 11 from both sides, get 2x squared equals negative 32. Then I'm going to go ahead and divide by 2 on both sides, and I get x squared equals negative 16. Now, to undo the square, I would square root. But the problem is when I square root the left side and I square root the right side, I get x equals plus or minus square root of negative 16. Now, the square root of 16 is 4, so we'd have plus or minus 4. But the square root of negative 16, I can't get to that because if I think about it and I say, okay, well, what's 4 squared? 4 squared is 16. What's negative 4 squared? That's also 16. So we can't really go ahead and find or square any real numbers that give us a positive or a negative number, I should say. We can't square any numbers and get negative numbers. So we got to figure out a new way of doing this. So what happened was a long time ago, mathematicians came up with the imaginary unit. The imaginary unit is I for imaginary, and I equals the square root of negative 1. So when we see a square root of a negative, I can simplify it using the square root of negative 1, take that out, and then it works out a lot better. The other big important thing to remember is that if I is equal to the square root of negative 1, I squared equals negative 1. So what's going to happen is when I see a problem like this, a square root of negative 25, I'm going to break it down, and I'm going to break it down into the square root of 25 times the square root of negative 1, because 25 times negative 1 is negative 25, and so I can do that by all means. And then I simplify one more time. The square root of 25 is just 5. The square root of negative 1 is I. And so the square root of negative 25 is just 5i. Now, when we have perfect squares like here, square root of negative 49, I can just go ahead and say that it's 7i. When I see something like the square root of negative 48, I need to break it down. And in this case, I'm actually going to break it down into the square root of 16, the square root of negative 1, and the square root of 3, because 16 is a perfect square that goes into 48. 16 times 3 is 48. And then I throw that negative 1 in there. Now, I wrote it this way because when I simplify, I get 4i square root of 3. Usually we put that I in between a number or in front of the radical. The reason being, if I wrote it like this, square root of 3i, it's kind of difficult to tell if that I is underneath the radical or not underneath the radical, and as mathematicians get lazy and sloppy, they're going to sit there and start drawing this faster and quicker, and it's just going to sneak in underneath the radical. It's not underneath the radical, so we need to go ahead and make sure that we put it in front of the radical and write it like I did here, 4i radical 3. Last equation here, or last function, expression, I'm going to break this up and say square root of 4, square root of negative 1, and square root of 5, because 4 times 5 times negative 1 is negative 20. That's going to give me 2i times the square root of 5. Okay, so now that we know how to simplify this, let's go back to our original problem from the first page. And when we get to this point, we have x equals plus or minus the square root of negative 16. Well, now what I can do is I can go ahead and just simplify that and get x equals plus or minus 16 is 4, and then negative 1 is I. So I get x equals plus or minus 4i. And now I have two imaginary solutions to this problem. Imaginary solutions allow us to have, solutions to problems that before could not even be solved. So that's kind of helpful in that regards. Now that we've invented this whole new number system, we have to kind of be able to add, subtract, and multiply and divide with those. And it's not too difficult, especially when we add and subtract. When we add and subtract, we just go ahead and treat the I like any other variable. And so if I see 2 plus 3i plus 5 minus 2i, I would just combine like terms. So here's a 2, here's a 5. They don't have any i's attached. 2 plus 5 is 7. And then I got 3i and negative 2i. So 3i plus negative 2i is just 1i. So 2 plus 3i plus 5 minus 2i is 7 plus I. I added the real parts, 2 and 5. I added the imaginary parts, 3 and negative 2. Over here, when I see a problem like this, what I'm actually going to do is I'm going to change it to an addition problem. Okay, I can usually add a little bit better than I can subtract. So when I do that, I've distributed that negative, and now I have 2 and negative 5. 2 plus negative 5 is negative 3. I can also go back and look and say, okay, now I got 3i plus 2i, and I get 5i. So 2 plus 3i minus 5 minus 2i turns out to be negative 3 plus 5i. Again, when I go ahead and multiply, we treat that I just like a variable with one little twist at the end. So we got 2 times 5, we got a FOIL, so that's 10. Then we distribute the 2 to the negative 2i, that's negative 4i. Then the inner ones are 3i times 5, which is positive 15i. And then the last term is 3i times negative 2i, which is negative 6i squared. Now, if you remember from the other page, back over here, I squared equals negative 1. So when I do that, I need to make this a negative 1. Well, that gives me 10 minus 4i plus 15i minus 6 times negative 1. Well, what's negative 6 times negative 1? It's just plus 6. So I'm going to have 10 minus 4i plus 15i plus 6. And then combine our non-real or our real terms. 10 plus 6 is 16. Negative 4i and 15i is 11i. And that's my solution. Now I could have done this a little bit quicker, and I'm going to show you a quick method here. When I FOIL and I get this 10 minus 4i plus 15i minus 6i squared, what I do is I always go and take my red pen, cross out any I squareds, and what's negative 6 times negative 1? Positive 6, and I change that sign. And then I just go ahead and finish the problem. 10 plus 6 is 16. Negative 4i and 15i is 11i. And I end up with the same problem, same answer, and it's a little bit easier. Okay? The last thing that we're going to do with these complex numbers is divide them. And dividing can get a little tricky. Dividing is kind of like what happens when we have square roots in the bottom. You can't have square roots with fractions in them. You also can't have square roots in the denominator of a fraction. But we can't have i's in the denominator of a fraction either. So in order to get rid of the i's, we're going to multiply by what's called the complex conjugate. Now when we're working with square roots, we just multiply by the conjugate. But same idea. We're going to take the opposite of that sign. So if it's a plus, we change it to minus. If it's a minus, we would use pluses here. All right. And then we just FOIL. All right. And I'm multiplying by 1, essentially, 3 minus 4i over 3 minus 4i. So that's fine. And when I multiply, what's going to happen is on the bottom, our i's are going to disappear. So just let's FOIL these through. 2 times 3 is 6. So there's 6. Then 2 times negative 4i is negative 8i. Then we got 5i times 3, which is 15i. And then we got 5i times negative 4i, which is negative 20i squared. All right, we're seeing that I squared, so we got to be careful. On the bottom, if I FOIL, I got 3 times 3, which is 9. 3 times negative 4i, which is negative 12i. 4i times 3, which is positive 12i. And then the last term is 4i and negative 4i, which is negative 16i squared. So I'm going to go get my red pen here. I see an I squared here, so I cancel it out. I make this plus 20. See an I squared here, so I cancel that out, make it plus 16. I also notice that since this is negative 12i and this is positive 12i, they're going to cancel as well. And if you notice now, the bottom, or the denominator, has changed to just 9 plus 16. All right? All my i's are gone out of the bottom. On top, I got 6 plus 20, which is 26. And I got negative 8i and positive 15i, which is plus 7i. So now I have an almost simplified problem here. I'm going to say 26 plus 7i over 25. And I want to put it in a plus bi form. So I need to split this up one more time and say 26 over 25 plus 7 over 25i. That's our final answer, and that's in a plus bi form. So we just go through. Oh, what happened here? Okay, this is fun. Oh, there we go. Whew. It was kind of close. Kind of cool, but kind of close. So sorry about that. We reviewed on how to add, subtract, or multiply and divide these complex numbers. The biggest thing being dividing when we multiply the top and the bottom by the complex conjugate. So hope that helped. Hopefully we'll be able to work with these a little bit in class, and we'll be good to go. So thanks a lot.